Okay, so I have the pleasure of introducing Professor Kulkarni, professor at San Francisco State University. She will talk about large text searches. Let's welcome the speaker.
Thank you for the introduction, and thank you guys for coming here. So I am Anagha Kulkarni. I am an assistant professor at SF State. And before that, I graduated, so I did my PhD at Carnegie Mellon on the East Coast. So CMU campus was more like this and less like SFSU. So I was taking a stroll around, trying to remind myself of the old nice memories. So, all right, let's get into it. I work in the technology that's behind search engines. So is there anyone who hasn't used a search engine? Yeah, well, no one, right? So let's start with that. Search systems are all around us. They are such an integral part of our life, right? There have been many surveys, many studies that have concluded that search and communication are the most widely used applications of computers. No surprises there, right? Lots of communication happening through computers and lots of search, trying to get to certain information that we need. Yeah? What's interesting for us as engineers and scientists is the broad spectrum along which, in terms of scale, along which these search systems fall. So on the one end of the spectrum is the small-scale search systems. These are usually characterized by low data volume, low query traffic, and query latency. So query latency is query response time. Okay? So in this scenario, we are searching for some file on our personal computer. Right? We are a lot more tolerant in terms of how quickly we find the result. Okay? But on the other side of the spectrum, we have the web scale search systems. Okay? And there we are actually less tolerant in terms of how much time we are willing to wait for the results to come back, right? Because Google has trained us to expect answers in the blink of an eye, right? So we get very agitated if it takes longer than a few seconds. Okay? But what's amazing is how much data volume Google Bing is processing, right? Petabytes of data, millions of queries. Latency has to be less than a second. And to support all of that, they have usually a big infrastructure supporting it, right? Data centers. Have you guys heard of that? Those are big computer farms, basically, trying to push through, trying to process all the query traffic that Google gets. So that's the other end of the spectrum. And in this talk, I want to focus on actually what sits in the middle, somewhere in the middle. So, and the users of these large-scale search system, as I call them, is people like me, my research lab. Okay? I do have data sets which are terabytes of text. So it's not small. Okay? It's lots of data. But I don't have as much query traffic as much as Google does, right? And I'm also willing to tolerate more slow response time. Okay? So query latency is not as big criteria. And the biggest thing is that I'm limited in my computing resources. I don't have a data center to process terabytes of data. I have probably a handful of cores that I can use to process this terabyte of data that I have. Okay? And what's important to realize is this is growing. People who fall into this box is growing. There are more and more organizations and enterprises that want to do this, that have growing amount of data, and they don't want to keep adding more and more computers, because adding more computers means, well, maintaining them, right? Powering them. So all of those costs add up. And so I want to support these kinds of scenarios where you have limited computing power, okay? But you want to do search at terabyte scale. You want to work with large data sets. That's where the name comes from in terms of the large scale. Okay? So that's my focus. All right, and like I said, that category is growing. Many research labs want to be doing that, many enterprises, organizations, and there are many applications where you have the search tier, the underlying search tier, and then a specialized application that makes use of the results from the search tier for very specific things. So medical decision support systems, usually they have one of the first things in their pipeline is a search. Okay? And again, there's agricultural, railway networks. There are intelligent tutoring systems that want to do a large search on big data sets. I don't know how many of you heard about this. This was a few years ago, but this was a really big news for language technologies when IBM's system called Watson was able to defeat a human in the game of Jeopardy. Okay? And one of the first things in their pipeline, one of the first things that Watson does is a massive search on several documents. Okay? So the summary of all of this is all of us, many of us, need to search big amounts of data, okay, at some point or the other. All right, so let's see how it is typically done. So the classic search architecture for a large-scale search is this. So that big cylinder up there, I'm using to represent the big document collection. Okay? And so the first step that's done is partitioning. Okay? Divide and conquer. Break up that big collection into smaller collections. And those are oftentimes called shards, the smaller sub-collections. Okay? And they are usually divided randomly. Okay? So a document goes in any of the hundreds or thousands of shards that are going to get created. So that's the first step. And then a dedicated computing resource. So the processor, network, everything, a dedicated system is assigned to each shard. Okay? And when a query comes in, okay, whenever a user types the query and hits the enter button, it is broadcasted to all of these computers through a controller. Okay? And what do you think would be the next step? Tell me. Yeah.
Would it go computer to computer doing linear search for each one to find what it wants?
Okay, good. So I'm glad I asked the question. So no, that's not what is going to happen, and maybe I didn't frame my question correctly. But what's happening here is the query is broadcasted. It's going. So let's say the query is March Madness. Okay? It's going to be sent to each of these systems. Right? So each of them has become like a small search engine. Okay? So each one is going to search for March Madness documents in each of these shards individually, independently. Okay? And so I was asking what would be the next step? Yeah.
To decide which one's most relevant?
Oh wow, you guys are ahead of what I was going for. No, actually, it's a very much simpler than that. What's going to happen is each of them is going to return a result list. What does Google return when you type March Madness? It gives you those 10 blue links, right? So each one of them is going to give us 10 blue links. Okay? And then the controller's job is to merge, let's say 100 10 blue links. Okay? That's all that's done. And the complete result set is returned to the user. Okay? So it's basically just a distributed system. Instead of having one computer processing March Madness through that big collection, we are delegating the task to 100 different search systems just to make things go fast. Okay? All right. So that's the traditional way of doing things. Okay? Traditional way of doing a large-scale search. All right, and this we are going to refer to as exhaustive search, okay, because it searches the entire collection. Right? Okay, so like I said, this is a distributed system, right? So it has all the good properties of a distributed system. Okay, it's usually fault tolerant. If one of the system goes down, well, the user still gets some results, right? Because not unless all of them go down. It's also good at balancing load, right? Because it's distributing, it's broadcasting the query to all the systems, all the computing systems in there. Okay? It's also simple and extendable. It scales well horizontally. Okay? But here's the problem. It's expensive, right? You need a lot of computing power to power this system. Okay? It needs a lot of processors, networks. And that's one of my constraints. I, as the research lab head, I don't have this kind of a computing power. Okay? And so what if I have only a few computing resources? Can I still dream of searching the big data set? Okay? And so that's the large scale scenario. So here's my goal. I want to do a search of a large collection efficiently. So I don't want to make the user wait there for an hour, right? I still want to do it quickly. And I want to do it in low resource environment where I don't have a lot of computing power. Okay? And I also do not want to ask the user to compromise on the search quality. Because oftentimes, if you want this, then you have to sort of make a compromise on the search quality. That if you want things fast, well, the results might not be that great. Okay? So I'm setting up myself for a tall order here. But that's what I'm going to do. And here's what the approach that we have proposed. We call it selective search as opposed to what I showed you earlier, which was exhaustive search. Okay? All right, so here's what we do. We take that big document collection and we still do partition it. Okay? But we are going to be clever about how we partition the documents. We are going to try and put documents that are similar to each other in the same shard. Okay? And I'll tell you on the next slide why that is. Why do we care about document similarity? And then the next step is when a query comes in, I'm not going to broadcast it to all the shards. Okay? I'm going to be selective about which shards are searched for that query. Okay? So, and how do we do that? Because that's a tricky problem. Okay? And I'll talk about that in a bit. And once we have identified those shards, I can send the queries just to those shards and get back the results, merge them, and return them to the user. Okay? So look how many, even in this toy visual, there are much fewer computing resources needed in this approach than in exhaustive search. Okay? All right, so that's the plan. So let's look at the first question. Why are we partitioning the collection based on document similarity? Okay. All right. So we are doing that due to this, due to what this guy said in 1979, which is still true. Okay. What he said is similar documents tend to be relevant to the same request. Okay. And let me show you an example of what that practically means. So I have this document A. Okay? It's about March Madness, right? Clearly, I don't know how many of you can read, but hopefully some of you in the front row. March Madness ratings, highest in 19 years, and so on. Okay? So we as humans would, I think, mark that document as relevant to this query. Yes? Right? Okay. Now, if I have another document, document B, again, March Madness 2013, how to watch Pittsburgh versus blah, 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 I would say this is also relevant to this query. Okay? But notice that these two documents are also similar to each other. When I say similar, In the most simplest form, the similarity function looks at which are the common words or how many common words there are between two documents. Right? So March Madness, basketball, matches, there will be a lot of common vocabulary on both these documents. Okay? So these two are relevant to the query and these two are similar to each other. Right? As opposed to this document, which is very unreadable. It's about IRS, tax filing, and all of that, right? We just did the tax filing. So I think all of us would agree this is not relevant to the March Madness query, and also that this is not similar to either of those documents, right? So if we put documents that are similar to each other in one group, if we cluster them together, right? Then, so right now I have two clusters, right? One is this tax-related one. The other one is basketball-related one. Yeah? And I think most of you see where I'm going with this, right? March Madness query doesn't need to be sent to this document collection, right? There are no relevant documents. So the only thing we need to search is this collection over here. And that's the point behind cluster hypothesis, that if you arrange your document collection such that similar documents are together, then you don't have to send the query to everyone. You can be more selective about which document collection gets the query. Okay? All right, so that's where March Madness would go and not here. All right, now that I have convinced, hopefully most of you, that sharding, partitioning the collection based on similarity is a good idea, let's try to look at how do we go about partitioning a big document collection. So we have, let's say, M documents, and that we want to partition into K groups, right? Such that each group is homogeneous in terms of the topic that it relates to. Right? So oftentimes this is what happens, that when you do similarity based grouping or clustering, some inherent topics emerge. Okay? Like all the politics related document might get clustered together because they have common vocabulary, right? Celebrity related documents will get clustered together, sports, and so on. Okay? Which is why we call these topic based shards. Okay? All right. So the key challenge here in getting from there to here is the size of the data. Okay? Trying to group documents based on similarity is, if done exactly, it's an NP-hard problem. Okay? And so how do we do that? How do we take a big collection of millions of documents? Actually, the largest document collection that I work with is 500 million, 500 million documents. So that's a lot of data to process, right? And each of them is a web page, okay? Not just like one record. So this is a real problem, a real challenge. And so for that, what we have to do is some approximations. Okay? And for one of the approximations, we use this law. Okay? So Heap's law tells us the rate at which new vocabulary is discovered tapers off as more documents are examined. Okay? So, which is logical, right? If think of this like a kid, okay, who's just starting to learn reading. Okay? I don't know if that's the best analogy. But if you're reading a document and making note of all the unique words in it, right? Then if you found X new words in the first document, it is highly likely that the next document that you scan would have less than X new terms, because you would have already discovered these X vocabulary terms, right? And so that's what Heap's law is trying to tell us, that as we keep scanning more and more documents, the number of new terms that we come across is going to taper off. Okay? So here's a plot from one of the data sets that I work with. And this is the sample size in percentages. Okay? And this along the y-axis is the average OOV. So OOV is out of vocabulary terms. Okay? Out of vocabulary terms per document. So what this is trying to show you is if I have scanned just a very small fraction of the collection, right? Only 0.05 documents. I have only looked at those many documents and have discovered some vocabulary. Okay? Even at that small sample size, there are only 5 terms in a document on an average that would not be in the vocabulary that I have found from this sample. Right? Pretty surprising given how small the sample size is. So what this is telling us that you don't have to look at the complete document collection to discover a large portion of the vocabulary. Okay? So we are going to use this to motivate what I'm going to do next, which is take the complete collection and then do a simple random sampling. Okay? So simple random sampling is reaching out into the bag and just grabbing whatever comes first. Okay? So random with uniform distribution. So I'm going to sample a very small subset from the complete document collection. Okay? And I'm doing that because I want to apply these computationally expensive algorithms. K-means is a clustering algorithm. Have you guys, anyone heard of this before? Some of you? I see some heads nodding. It's an algorithm that will do those similarity-based clusters for us. Okay? So when I give this bucket of documents to K-means, it will give me K different buckets. And each of those buckets will be homogeneous in terms of the topics. Okay? And like I said, these are computationally expensive. Okay? So I don't want to run this algorithm on the complete collection, which is why the sampling. Okay? So I take a small sample and apply K-means. And what comes out is what is called as centroids. Okay? Topic centroids. So centroids is basically, what would be a good analogy for centroids? They are a way of describing what's inside the sports bucket. Okay? Let's say there's the sports topic. Okay? And so the centroid is like a summary of the sports bucket. Okay? It's not the complete bucket, it's the summary. Okay? And the same kind of summary, you'll get a summary for each topic. Okay? So that's what comes out of the K-means algorithm. Okay? Once I have these topic centroids, now I go back to my complete collection, okay, the big one. And now these centroids are going to help me put the big collection into shards. Okay? Doing this is cheap. Okay? But doing the complete K-means on the big data set is very expensive. Okay? So we did this workaround. So we're going to use topic centroids to filter these documents into the buckets. Okay? So now we have these topic-based shards. Okay? All right, so we have been calling this approach sample-based K-means. Okay? All right, one problem with what gets created with this approach is the distribution of the shard sizes. Okay? We are not controlling how many documents go in each of those topic buckets. Okay? And this is what happens. Some shards are really small and some shards are really big. Okay? This is not good for several reasons. And one of the most important reasons is the query runtime. Okay? If a query gets sent to one of these, it's going to be a quick turnaround. Okay? But a query gets sent to one of those, it's going to take a while. Right? And usually users don't like variance. Right? They like consistent performance. And so we had to figure out a way to make this graph more balanced, more uniform. Okay? And so we came up with a very simple approach. It's just a multi-step iterative process where we identify which are the large shards, okay, and apply k-means to them again to identify which are the subgroups within them. And then at the end, we also identify small shards, okay, that are too small. So we have certain target shard size, okay, and so the shards that are way below that are small shards. And those we merge together with not large shards. And at the end, we compared, did we get what we were hoping for? And our conclusion was yes, because so in this histogram, we are comparing the original sample-based k-means with this size-bounded sample-based k-means. Okay? And this was our targeted range, that we want to stay within this range in terms of shard size. And what we saw is using the second approach, more than 70% of our shards were in this category. Okay? In the previous category, there were a lot of small shards and also a few big shards. Okay? So this big tower is good. Okay? That most of our shards are now close to the range that we want. Okay? All right, so now that we have our shards, topic-based shards, the next question was, when a query comes in, how do we figure out which shard should it be sent to? Okay? And for the first part of this talk, which is what we are in right now, I'm going to use an off-the-shelf, an existing algorithm to tell me for this query, for March Madness, this shard and that shard should be searched. Okay? So right now, we are going to use that as a black box. Okay? And then in the second part, we will open up that black box and try to see what we can do. Okay? All right, so we have solved for now, as best as we can, the document similarity problem. And then for this one, like I said, we are going to use the ready algorithm, an existing algorithm, and its name is ready. Okay? All right, so that's the one. So here's another example. Instead of March Madness, there's the celebrity Justin Bieber. And so ready knows or can figure out, okay? It's an estimation algorithm. It makes mistakes as well. Okay? There's no human here. But it can tell us with some amount of guarantee that those two shards, S2 and S3, should be the ones that are searched for this query, because that's where most of the relevant documents are for Justin Bieber. Okay? All right, so that's what we're going to do. But the next step is, how do you actually search? Once you know that S2 and S3 should be searched, how do you actually search? Because I don't have Google, right? So I'm going to use an open source search engine called Indri to execute the query against shard S2 and S3. Okay. All right, so that actually is the complete architecture of the system. Okay. So this was k-means based approach. Then this is going to be ready and Indri, okay? And outcome, the result, the ranked result. Okay. All right, so now that we have put this all together, how does it actually perform? And so to test that, we are going to make use of 3 data sets. Okay? These are the 3 data sets. Gov2, I call this category B for short, and this is the category A, okay? ClueWeb 09 English. So all of these are web pages, but the first one was restricted to .gov web pages. Okay? And it's also the smallest data set in my experiment. So the smallest one is 25 million. Okay? So that's not small. This one is 50. This is, like I said, 500 million documents. Okay? And then we need queries, right? Just the data set isn't enough. We need to evaluate how well my approach does for an actual query, for which we know that these documents are relevant and these are not relevant. Okay? So we need a query set, a special query set for which we know what the relevant documents are in the particular collection, in the particular document collection. Okay? And so those are the statistics for that query set. So I have 150 queries for gov2 and then 100 queries each for the ClueWeb datasets. Okay? These are very similar to web queries. So on an average, web query is about between 2 to 3 words long. Okay? And so these are also in that ballpark. All right. And here are some numbers about how many shards, because each data set is first divided into these topic shards, right? So for gov2, I had started, and these numbers had some reasoning behind them. I'm not going to go into those right now, but I started with 250 shards, and after doing that merging, splitting process, I ended up with 208 shards, okay? All right, and then for this one, it was 98, and for the largest one, it was 800 plus shards. All right, the other thing we need to know is how we are going to quantify the performance. What are going to be the metric that we use, okay? So there are usually two types of metric that are used, the accuracy and cost, okay? Within accuracy, we are going to use three metric, okay? Precision at rank 10, and this is the easiest one to understand. So we look at the top 10 results, okay? And remember, these are special queries. And they're special because we know the truth. Okay? We know the ground truth. We know which documents are relevant and which are not. Okay? So each of those results that are returned by my approach or the baseline approach, we can look at them and say the first one is relevant. The second one is not relevant because we have that data already. Okay? So precision at 10 tells us how many documents of the top at the top 10 ranks are relevant. Okay? That's precision at 10. The next one, right. So for this example, the precision at 10 would be 0.3, okay? Because it's 3 divided by 10. All right. And then NDCG is slightly more complicated. NDCG not only models relevance or non-relevance, it doesn't do just binary categorization. It also takes into factor the grades. There are sometimes shades of relevance, right? Some documents are really, really relevant, and some shouldn't be retrieved at all, right? So it takes into consideration those grades of relevance as well. And it penalizes, the score gets dinged if these really good or really relevant documents are not at the top of the rank. Okay? So in ideal situation, we want the really relevant documents up at top, right? At the top rank. We want them to be bubbled up. And if they're not at the top, then NDCG will reflect that in the score. Okay? All right, and then the third one and the last one that we look at in the accuracy category is MAP. And MAP is an average, an aggregate metric because it combines the performance on all the queries. So remember, for gov2 I have 150. So MAP gives us one number for all the 150 queries. Okay? So it's easier to compare two systems if we are working with just one number instead of 150 numbers. And then the cost we are going to keep simple. We are going to compare the two search systems, the exhaustive search and selective search system, based on the number of documents that get evaluated per query. Okay? So lower is better, right? All right, so let's look at the results. So this is for the smallest data set, the gov2 data set. Okay? And like I said, we are looking at two systems. The baseline is the exhaustive search. That is the current standard, industry standard. Okay? And selective search is the one that I proposed. So before I show you the results, what do you think, what's your intuition? Given that exhaustive search looks at the complete collection, right? Searches the complete collection for any given query, right? Versus selective search in this particular case is going to search 20 shards, those 20 small buckets out of the 208 buckets. Okay? So what do you think in terms of search quality? Which would be better? Exhaustive search, right? It's looking at the whole thing, right? Whereas selective search is looking at a small subset. So the search space of selective search is much smaller than that of exhaustive search. So search quality-wise, we expect exhaustive search to do much better. Okay? And efficiency-wise, cost-wise, selective search to do better, right? Because, well, the search space is small. We are doing less work. Okay? All right, so let's look at what happens empirically. That's what we expect. Some surprising things. So selective search isn't doing worse than exhaustive search, right? A tad bit higher, but that's not statistically significant. So I'm not going to say it's doing better. Okay? But it's not, certainly not doing worse than exhaustive search. Okay? Same for NDCG and same, more or less same for MAP. Okay? This one is especially tough. Okay? When I showed these results to my advisor, it took a while for him to come around and believe this actually. That they can be doing just as well even on MAP. Okay? Because it's a tough metric to perform well on. And let's look at the cost now. So here things are as we would expect. So exhaustive search, on an average, searches 3.63 million documents. Okay? So for this data set, there are 25 million documents in total. So out of those, on an average for a query, exhaustive search looks at those many documents. Selective search looks at a very small fraction of that. And so in terms of savings, selective search has 82% saving. It's doing much less work, which is not surprising, right? So that part is not surprising. This part was surprising. Okay? Any guesses why that's happening? Any bug in the code? Or something more than that? Remember how we organized the documents? The two March Madness documents were all together, right? And so really, if in my toy document collection, if those two documents are the only ones about March Madness, and if I direct my query to that shard, then am I going to lose anything by not searching all the other shards? No, right? And that's what is happening here, that we are being clever about where we are searching. Right? Have you heard of that little story that if you have lost your pin and if you're looking under the lamppost because there is lamp, right? And not looking where you actually lost the pin, okay? That doesn't make sense. Just because there's lamp, you wouldn't search there. So we are being clever about how we organize our documents and where we search things, okay? And that's the reason. And these trends continue with the other two data sets as well. So I have remembered 3 data sets. The last slide was just one, the smallest data set. This is the medium-sized data set. Okay? Again, very similar trends. And the search cost savings actually increase as the collection becomes larger, which is the perfect trend that we want. Okay? And this is the largest data set, the 500 million documents. Okay? And that one had a really surprising result. Okay? This difference is actually statistically significant. So selective search is doing better in terms of search quality than exhaustive search. Right? So searching less documents, we are doing better than searching all the documents. I see some of you trying to think, why? Right? Why? How is that possible? And the only thing I have been able to come up with is we reduce noise when we do this clever clustering, right? We reduce the noise in our search space. Because March Madness, going back to that query, there might be a document that's not about March Madness. Okay? But in fact, there is something that happens up in Seattle, I think, during March. I think it's a rowing competition or something. And that also gets popularly called as March Madness, but it's very local to that region. Right? Most likely, if the user is not from Seattle, the March Madness sense that he or she is referring to is the more common sense, which is the basketball one, right? So in that case, maybe we were able to get rid of that rowing-related March Madness document, which Exhaustive Search was not able to. And I have actually one slide that tries to show that. But before we go to that slide, I realized I didn't show you the search costs. So like I said, the search cost savings increase as the document size increases, which is really great for us small research labs, because as our data set grows, the search cost is not going to linearly increase if we use selective search. Okay. All right. So I also did some experiments later on in terms of runtime, because the cost is in terms of documents. So I'm using number of documents as a proxy for an actual query response time. And what I saw with my small experiment using query response time, that the savings in the query response time with selective search is much smaller than that of exhaustive search. Okay. All right, so here's that qualitative analysis. Why is selective search doing better in terms of the search quality? So one of the queries is Obama family tree, okay? And precision at 10 with the exhaustive search is 0.5, and precision at 10 with selective is 0.9 for this query. Okay? So in exhaustive search, 5 of the top 10 results are not relevant. Okay? Whereas in this case, only one of the top 10 results is not relevant. Okay? And why is that? So here's how the exhaustive search looks. Okay? The first ranked one is relevant, the second one isn't, and so on. Okay? And then I went into the shards and tried to see where these documents are. Okay? So this one I don't care about, it's relevant, it's fine. Okay? But this non-relevant one, which is in the exhaustive search, is in the shard that is at rank 4. So we didn't search the shard in the selective search framework when we had sent the Obama family tree query. Okay, so the Obama family tree query got searched only at the top 3 shards. Okay? And so this non-relevant document was not in that search space, so it did not get included. Right? Similarly for this was in a shard that was way below. Okay? It was in the top 3 shards. So we are able to get rid of these documents which are noisy, which are false relevant documents. Okay? All right, so that's the end of the first part. And I'm looking at the clock. And I'll be happy to stop here as well, because this is really the main part of the talk. There is a part 2. What would you recommend? Keep going or?
5 more minutes.
Ha. All right. Okay, so let me summarize this. So the part 1 that we saw right now, the focus was how do we do this sharding, the partitioning of the collection. Okay? And what we saw is that this topic-based organization of documents concentrates relevant documents into shards, and as a result, it can facilitate effective and efficient search. Okay? And so we also saw, using the empirical analysis, that doing selective search doesn't degrade search quality like we thought initially, and it does decrease the search effort substantially. All right, so the next part was going to be shard selection. So remember, in the first part, I had made use of this off-the-shelf algorithm called Ready to tell me that if Justin Bieber is the query, then go to shard S7 and S11. Okay? And so in this part, if we had more time, I would have told you how I have solved this problem now. Okay? But I think we won't be able to finish the whole thing. So I don't know, this is, I know, your last seminar talk, so I don't want to stretch it out for you. Should I stop right now? Or are you very curious about this problem?
Well, maybe you're curious, maybe you can ask questions.
Yeah, maybe we can do that. Okay. So I'll skip over to the last summary slide. And so one of the things that gets me really excited about this work is if we, research labs, are able to work with large data sets, that improves our credibility. So over years, most of the big conferences in IR, information retrieval, which is what the formal term is for search engine research, okay? Most of these conferences have more and more papers from industry. Okay? Guess why? Because they're sitting on gold mine. They are working with large data sets because they have the computing power. Okay? And the other big reason is they have these amazing query logs, right? They know what each of our query is, what we are clicking on, how long did we scan that result, all of that. And now compare that to my research lab. What do I have? Zilch, nothing, right, of all of that. And on top of that, if I say, well, I'm a small research lab, I can only work with 1,000 documents, no one takes me seriously, right? So being able to work with large data sets is really important if you want to make any difference. And so I'm really happy about this part, that this is going to improve the credibility of my work, and for people who want to work with large data sets and can't if they are restrained in terms of how much computing power they have. So that was one of the good parts. And the other thing that I like about the approach that was proposed is it doesn't depend on any external resources. Okay? All it does is really work with the document collection, use a clustering algorithm that is clever about where documents are put. Okay? We are not using any external handcrafted taxonomy, ontology. Okay? So anyone and everyone can use this approach. So that's another thing that I'm proud about. All right, and then of course the savings. So you saw 90% savings in search cost. Right? That can translate into many things. Okay, reduction in how much money is required, and also in terms of how much power is required. So there are many different aspects of this. All right, and so it was really nice to see that to get that cost saving, I'm not compromising on search quality, on search effectiveness. In fact, in some cases, selective search does better than exhaustive search. So that's all. I think I'll stop here and I'll take any questions you have. Thank you.
Out of time, unfortunately.
Oh, we are out of time for question as well? Okay. Well, can I take one?
So the results obviously depend on the quality of ground truth, so how you determine something is relevant or not. So could you tell us where did you get the ground truth?
Yeah, good question. It's actually done by an independent source. Have you heard of NIST, the National Institute of Standard and Technology, right? So they create the evaluation. So they hire 3 or more assessors, humans who do the relevance judgment. Yeah, I pity them because their task is look at March Madness, look at these 100 different documents and say this one is relevant, this one is non-relevant. And not just one, but 3 or more people do that. And they then look at inter-annotator agreement. And if there are some queries for which those 3 people disagree big time, then they actually discard the query. So these queries are really solid queries that get used by a big IR community.
I see.
Yeah.
That makes sense. And the quality of, the selective approach works great for the top 3 shards that you use. How did you come up with number 3?
Right. That was the part 2. That was another contribution that I'm proud of, because until then, most time it was just a random choice that I'm going to pick, I'm going to search the top 5 shards, or I'm going to search top 10 shards. But what I have tried to argue is that we can't make this choice keeping the query out of the picture. It has to be dictated by the query, because certain queries are very specific, others are more general, and so the query should be driving how many shards you search. Yeah, that was going to be the second part. Good questions. Yeah.
Okay, thanks.